Our next goal is a theorem you probably already know. The theorem saying that the multiplicative group of a finite field is cyclic. To make it instructive, I will prove it in a slightly more general version. So let K be a field and G a finite subgroup of the multiplicative group of K. Then G is cyclic. And let us prove this. The idea is to compare G and the cyclic group of order n, where n is the cardinality of G. So let me denote psi of D, the number of elements of order G in G. So we need to prove that psi of n is non-zero, and we know that n is equal to the sum of those psi of D. And let me denote phi of D, the number of elements of order G in Z over Nz. But Z over Nz is a cyclic group, and it contains a single subgroup of order D, which is itself cyclic. So, as Z over Nz contains a single cyclic subgroup of order G for each D dividing n. Well, namely, this is the subgroup generated by n over D. So the one generated by n over D. This phi of D is also equal to the number of generators of Z over dz. And this is well known to be the number of numbers between 1 and D minus 1, which are prime to D. So we know, of course, that phi of n is non-zero. So I claim that either psi of D is 0 or psi of D is equal to phi of D. This is, of course, sufficient. Since the sum of the phi's and of the psi's must be equal. So, proof of the claim. If there is no element of order g, then of course psi of g is 0. If there is no element of order g in G, then psi of G is 0. If there is one element of order G, in G, then this x is a root of the polynomial x to the power g minus 1. And if you look at all the roots of such a polynomial, you see that they form a group of this polynomial, form a cyclic subgroup of G. So G, as well as Z modulo NZ, has a single subgroup of order G, or cyclic, well, which is cyclic, or no such subgroup as well, or no such subgroup at all. So this is a comparison between G and Z modulo NZ. But the difference is, of course, that Z modulo NZ has such a subgroup for any G dividing N. And G not necessarily, a priori. Okay. So this implies that if, well, this in fact implies the claim, if phi of G is non-zero, then there is such a subgroup and the number of elements of order G, phi of G, is the number of generators of that subgroup. Well, obviously this is the same thing as phi of G. So whenever psi is non-zero, it is equal to phi. Okay? Well, in particular, psi of G is always less or equal than phi of G. But in fact, there must be equality because the sum of those are equal. So the sum of psi's is equal to the sum of phi's. And then the psi's all must be equal to phi's. In particular, psi of n is non-zero, and we have proved the theorem. There is an element of order n and G, so G is cyclic. Okay, this has a couple of corollaries about field extensions. Corollary 1 is that if K is an extension of Fp of degree n, so K is f of p to the power n, then is generated by one element. There exists an alpha such that K is equal to Fp of alpha? Well, you might object and say this has already been shown. We have seen that Fp to the power n is a stem field of any irreducible polynomial of degree n. But this corollary is actually stronger, because when we have been discussing those stem fields, we did not say that such polynomials existed. So in particular, there exists an irreducible polynomial of degree n over Fp. Okay? This is the thing which we don't know yet. But the proof is, of course, very easy. Since we know that the multiplicative group is cyclic, it suffices to take a generator of such a group, of this group. So for the proof, it suffices to take for alpha a generator of K star. Okay. Corollary 2. The group of automorphisms of K, well, Fp to the power n over Fp is cyclic, generated by the Frobenius map. Well, Frobenius map F takes x to the power p. As we have already remarked, this is a field automorphism. Well, let me prove this. Of course, x to the power p to the power n is x for any x in f p to the power n. This we have already seen several times. So, Frobenius to the power n is the identity. On the other hand, the order of this Frobenius is exactly n. Since if m is strictly less than n, then f to the power m is not the identity, because x to the power p to the power m minus x is 0 has only p to the power m roots. And p to the power m is strictly less than p to the power n. So it cannot take all elements of our field to itself. Okay? Well, and finally, f p to the power n is fp of alpha, where alpha is a root of irreducible polynomial of degree n, so it cannot have more than n automorphisms. Well, this alpha, irreducible polynomial p, this alpha goes to another root of p under an automorphism, so there cannot be more than n of them. So the cardinality of this group is at most n. Well, then it is n, and the group is cyclic generated by F.